Okay, so this is the first video I've actually made in school, so we'll see how the sound comes out. We sort of left off here where we're looking at different tidal patterns all around the world. This should be kind of familiar to you. This is figure 915-ish in the book. I think it's 916 in some. In the pink, in the map portion of this, we're looking at semi-diurnal tides, which have been sort of zoomed out so you can see the tidal range and how they have all basically equal heights right in here. Oops. And then we also have the purple, which as you can see is much more common, is mixed tides. Mixed tides occur commonly along the west coast of the United States, parts of South America, even parts of Canada. If you notice in the Gulf of Mexico, there are actually areas that are also mixed. And then a very tiny bit right down there, that's semi-diurnal, even though it's classically thought of as diurnal. You can see the diurnal areas here. Ocean bowlers, that's something you should know. We talked before about the amphidromic point as well as the co-tidal lines representing the crest of the tidal wave that's being acted upon by Coriolis moving around and around. This is basically can be also called a rotary tidal current. Rotary tidal currents are due to that circulation of the tidal crest in and around the ocean basin. They're found offshore, open ocean area, and they're due to Coriolis, and they can actually sort of spin off of the larger co-tidal lines, and you get very odd little rotary currents. We don't get them too much around here, but in other places, especially open ocean, you do. They tend to move very slowly with the crest moving in and out, and you can kind of see that in this graph here, that you have the tide coming in and going back out. When that rotary current encounters the coastline, the friction causes the water to drag, and it sort of gets left behind. And because of that, it creates what we typically see as tides along the coast, where we have tide coming in and tide going out, because this water is being funneled in and out of topography, things like bays and estuaries. So words you need to know. You need to know that the ebb current is the outgoing tide, the flood current is incoming tide, and no current is called slack tide. Those are right here. And that these, where you have true ebb tide and true flood tide, that's frequently called reversing tidal currents, because one goes in, one goes out. And in some places, they can actually be a really big navigation hazard. There are places in the world where the currents, even though the rotary currents move very slow, because you have this funneling of a large amount of water frequently through a narrow opening, you get really fast-moving tides, sometimes on the order of 20-plus miles per hour. So they can be a real navigation hazard. Even right around here, Manasquan Inlet is considered a major navigation hazard, especially as the tides are changing. On the plus side, a lot of our bays are being damaged through sedimentation, and this fast speed of a lot of these currents helps slow that process down. The Bay of Fundy is sort of an important idea. The Bay of Fundy is always touted as being the largest tidal range in the world. It actually goes back and forth with a place called Ungava Bay. I think that's how you spell it. Ungava Bay is also in Canada. It's farther north. They just started recently measuring tide there. And the tide during spring tide for both of them is approximately 17 meters. They're statistically the same. And the largest area is actually in Minas Bay, and it's right here actually. It's the largest spot. It's a place called Burncoat. It's a little point that sticks out, and the tidal range there has been absolutely ginormous. In the 70s, might have been the 50s, there was a storm that kind of got funneled up the bay, and due to waves come in this way, as well as the tide, and then they refract, and they get funneled up the bay, which is why they get so absolutely ginormous. And then when they wrap around the points, like here, and the one that's right here, you get a lot of wave refraction. And this wave refraction can cause huge tides. The one along with this storm surge was over 70 feet tall, absolutely ginormous, which is odd because the tidal range at the mouth of the bay down at this end is only about 6 feet or 2 meters. It's all through topography and wave refraction that you get these ginormous waves. Another phenomenon that you can see associated with tides is whirlpools, and you get this where you have reversing currents. And what happens is, generally speaking, one current is moving out at the same time another current is moving in, and you begin to get this rotational effect. And these are real phenomenon. They actually happen. They can be very fast, 16 kilometers per hour. And there's a really famous one called the Maelstrom, which is in Norway. I'm going to try to open that up real quick. Let me see if I can do this. Hold on. Let me pause this. Okay, so I can't actually show the videos when I'm trying to make this at school. So I'll post, there will actually be 2 YouTube videos posted besides just the school one. There's one that will show you the actual, it's only about 20 seconds long. It's the Maelstrom in Norway, and it's actually a ginormous, fast-moving whirlpool. And it actually doesn't sit in one spot. It migrates along the river as the tides are moving, which is kind of scary. They can be really damaging to ships. The other video is of the Bay of Fundy, where you can see the tide moving. Next slide. The next thing I want to talk about is actually in the box. That's why it says 9.1 in the book. It's called a tidal bore. A tidal bore in a place with a large tidal range, like the Bay of Fundy, are not the same thing. Please do not confuse them. Tidal bore occurs when you have a flood current that comes up a river. It's usually a shallow river that's very narrow with sort of a sill. And you basically can get the tide comes in as a single wave. It's the true tidal wave, as it's referred to in the book. They can be huge, 5 meters high and 20 kilometers per hour. I put a video on the website of the tidal bore moving in Nova Scotia. This was small, only maybe half a foot high, but you can see that the tide comes in, instead of just rising gradually like it does around here, the tide comes in as a single wave, and when the wave goes past, it's high tide, and when the wave goes out, it's low tide. In the Amazon, they can be really large, and people actually surf them during the spring tide. And it's interesting because the wave travels for kilometers. So people ride them, miles and miles up the river. Grunion. So another box of interest in the book is grunion. Grunion are a small fish. They're common in along the west coast of the United States, Southern California, and Baja, Mexico. And they are an example of an animal that's closely tied to tides in terms of being able to maintain their biology. They actually come up out of the water. They wriggle up at spring tide, and they bury their eggs a couple inches into the sand, a few thousand. And they come out of the water to spawn. Now, the eggs hatch approximately 9 days after they've been laid. And if you think about what we know about tidal currents, if they come up at the end of the spring tide, about 9 days or closer to 2 weeks later, you will have another spring tide. And they begin to hatch the wave action, and then they immediately run back out into the water. And there's sort of there's a bunch of videos. I'll post one online of Grunion runs, it's called, when they migrate up to mate. Tidal power. I'm going to do this part quickly. You can read about it in greater detail in the book. Tidal power is a relatively new idea in terms of generating electricity, but it's been used for years for doing things like making flour or sawmills. You've probably seen in cartoons that wagon wheel looking thing next to a river or bay, and the tide runs in, spins a wheel, and can grind things. There's a lot of interest in it lately because it's a renewable resource, and there are a few places in the world that have exceptionally good resources for this. They need a high tidal range. It has very low operating costs. There's no fuel. I mean, everything is provided by the tide itself. There are some disadvantages, though. They only work when the tide is going in or tide is going out. In places like the Bay of Fundy, it comes in so quickly that it spins once or twice a day, and then that's it. There's also problems with biofouling, which is organisms growing all over it, which constantly need to be cleaned, and that can actually account for a lot of the cost of tidal power. There's a really famous one in France near the English Channel, and there's only one in the North America, and it's in the Bay of Fundy. There are a few other places. There's a map that has potential for high tidal power. You see there's a few all along the world. 6 is the one that's in the Bay of Fundy. Ungava Bay, which is the other very large tidal range, is up in here in Canada. That place is also being explored, and a few places in the United States. You can see that there just aren't that many places that have a large enough tidal range and the right conditions to favor this. But in those places, they can generate so much power. The one in Scotland powers something like a quarter of the entire country. And that's it for tides. 10 minutes exactly.